in advanced hydraulics, we're talking about something called friction loss or head loss. Now, what friction loss or head loss means, remember to us, head is the word for energy. And so when we look at the term head loss, loss means that we're not getting what we should. Friction is a form of energy. It's a heat energy. And so when we're talking about friction loss, we're talking about losing heat energy. Now, of course, the more heat energy that we create, the more energy we're going to lose. And of course, what that means is, well, we're using it too. And so therefore, our pump has to use more energy to supply that loss. So if we can keep those losses to a minimum, that's really going to help us. So you notice what it says in the bottom line. Loss means you are paying for something that you are not getting any use out of. And that's why we want to keep those losses to a minimum. And of course, the most important thing that we want to make you aware of is this should raise an alarm. This coming up here. Okay? So it should raise an alarm when we understand that we're losing energy. We're paying for something and not getting use out of it. That should raise an alarm to us. Okay? So we're going to start out next year by understanding where those losses all start and how they happen here. So here we're looking at a picture of a setup, and we're going to talk about the word deadhead. Okay? Deadhead is when the pump turns on and there's just nothing happening, no water moving. Okay? Deadhead is an indication of something that's happening on the discharge side of the pump. So when that pump turns on and something on the discharge side is plugged up and doesn't let the water go through, we now have a deadhead application. We're running the pump against a closed valve somehow. Say, for example, we're doing a sprinkler application and one of the solenoid valves doesn't open up. That's a closed valve, and that's definitely going to cause us a problem. Okay? So the impeller is spinning, but no water is moving. That creates friction. Remember, friction is heat, and heat's a form of energy. So you have to remember that on the suction side of the pump, because heat is a very good conductor of water, that heat's going to go down the suction pipe. And, of course, you have to remember that it's going to go down the discharge pipe, too, to wherever the plug happens to be. One guy mentioned to me one time that he had an impeller that melted down, deadhead of the pump, and he melted the impeller down. So he went ahead and he fixed it, put the pump back in the application, and he still wasn't getting any pressure at the sprinkler heads. He checked the pressure at the pump was working fine. So the next thing he did was he started taking things apart, and right at that first elbow, he found parts of that impeller, and that's what was preventing the water from flowing. Okay? So on the suction side, when you get a lot of heat, if you're using a plastic pipe, and here's the big word, if you're using a plastic pipe, this is what's going to happen. All right? And you can see there that that plastic pipe just absolutely collapsed. When the temperature of the water got this melting point of the plastic got soft enough, because we are creating a vacuum on the suction side, you can see we collapsed that pipe. And when you collapse that pipe, you're not going to get much water to come through there. And so that's why it's very important that we understand what's taking place when we deadhead a pump. Now, there are a couple applications, a couple things we could do to prevent deadheading the pump. We'll talk about them at another time. Okay? Now, we have to understand this is the suction side. This is the suction side of the pump, all right? But remember, just like that heat travels down that suction pipe, it's also going up the discharge pipe. However, on the discharge side, you can see what's happening here is that the pipe is swollen. Okay, you see that great big bloated area in the middle of that pipe. And of course, what caused happen? Well, what caused it to happen was the fact that we now have hot water under pressure. And of course, what's going to happen when that hole appears? What happens when that pipe gets so hot that it explodes? Because what happens is hot water comes flying out of that hole. And if you happen to be in front of that hot water, you're going to get scalded. All right? Now, I got to tell you honestly, my first job choice was not being a trainer. My first job choice was to be a cook. And I can remember getting out of the Navy, coming back home, getting a job at a restaurant, and it was my turn to boil the shrimp. Okay? So the first thing we did was we put water in the pan, and we put the shrimp in the pan, and we filled that pan almost up to the top. All right? Once we got the water in there, we got our shrimp in there, we throw a little oil in there, we would put some spices in there, and one of the things that we did, our little secret, was we put a little cinnamon in there. It really made the shrimp taste good. Okay? Now, the next thing, of course, that we did was we would take those shrimp and we would put them on a fire. So you turn the fire on, and of course, you walk away. There was an old saying in the Navy, I was in the Navy too, there's an old saying in the Navy that said, watch pots, don't boil. And I gotta tell you the truth, they do, but it just seems to take forever because you're watching. So you go and you find something else to do. Now, when the pot boils over, then it's time to take the shrimp off of there, walk them over to the sink, put them in the sink, and run cold water on them. So you get the pot to boil over, and you say, okay, now it's time to clean things up a little bit. And you go and you pick those shrimp up, and you carry them over to the sink. So I pick the shrimp up, and I'm carrying them over to the sink. Now, this is a true story, okay? It just so happened that there were some girls coming up, some waitresses coming up from the basement, and they weren't paying any attention to me. Because you see, when I was in the Navy, I was also taught that any time you're carrying around a hot pot, you always yell, hot, hot, so the people knew it. Now, of course, what we're seeing here next is that as I walked around the corner, one of the waitresses walked right in. Okay? Now, I knew I could not drop this pan of hot water because this water is at least 210 degrees. It might not be bubbling, but it's still really, really hot. And I knew that would really hurt us really bad. So I thought, I can't let go of this pot. I got to keep it up. Now, we're going to talk a little bit here about what happens. Okay? So we've got a direction of movement here. I'm moving in that direction going towards the sink, and all of a sudden, I stop. All right? It wasn't because I wanted to. It was because she stepped in between me and the hot pot of shrimp, and there was no place to go. So I stopped. All right? When you stop, what winds up happening? Well, you get some momentum build up, and that momentum is going to allow the water to move. So the pan stops because I stop. But the water in the pan doesn't stop. It moves in that direction of movement. And then, of course, what winds up happening? It comes back in the other direction. We call that water hammer in our business. Okay? So let's talk a little bit about what water hammer really is. All right? So water hammer is when you've got a piece of pipe. And on that piece of pipe, there's a valve. Piece of pipe is coming up here in just a second. All right? So there's a valve on the end of there. It can be a ball valve, a gate valve, whatever. So we've got a valve there. Okay? And the water is moving through the piece of pipe. Now, as the water moves through the piece of pipe, we have to understand that that water has weight, it has momentum, and it has pressure pushing it. Okay? So with the thought of weight, momentum, and pressure pushing the water, what happens is somebody closes that valve really fast. what's going to wind up happening is the water's going to hit that valve so hard, and it's going to come right back at its source, okay? When it does that, we call that water hand, all right? Because what's going to happen now is the pressure inside that pipe is going to build up. It can build up to the point where it can bust a pump, it can bust piping, so it can be very, very serious. And that's why we got to tell you got to be careful with water handling. You got to make sure that your system can handle any unexpected pressure boosts, because those unexpected pressure boosts are going to come from what we call water handling. Okay? So now remember, I stop, the pot stops, the water hits that side, and what's it going to do? It's going to come right back to the other side now. Okay? So when you see a pipe doing this, the first thing you want to do is turn that pump off and then run the heck out of there. Okay? Because if you don't get out of there and that pipe blows up, you could be hurt. All right? We don't want that to happen. So make sure that that if you ever are in a situation where the pipe bursts and that hot water comes flying out at you, just remember that first aid kit. Get those clothes off the front and get squirts. Okay? Now, of course, what we're really talking about here, and the reason this whole subject came up, is because we were talking about friction loss or head loss. Okay? There's three factors that make up head loss. The three friction loss factors are, in order, you remember factors, there's things involved. Okay? So the first one here is going to be the type of pipe. There's two types of pipes that we use in our industry, steel and plastic, and you have to understand that there's a big difference between steel and plastic. Steel pipe is a very porous material. Plastic pipe is very dense and very easy. Okay? The next thought here is the pipe diameter. Pipe diameter. Now, I want you to know this is what gets most guys in trouble, right here. They think they're going to save some money by putting a smaller pipe. What they really wind up doing is they wind up costing the customers a lot of problems. So we're going to strongly encourage you to make sure that you've got the right size pipe, okay? Because that's a huge factor here. And then, of course, this is probably one of the more obvious things, the length of pipe. The longer the pipe is, the more friction loss you're going to incur. I mean, that only makes sense. So those are the three factors that we have to take into consideration. Type of pipe, the diameter of the pipe, and the pipe. By the way, I want you all to understand, I did not tell you you should be using plastic pipe. I simply mentioned that plastic pipe has less friction loss than steel pipe. There are instances or occasions where you have to use plastic pipe or steel pipe, and when you do, just make sure you account for the friction loss. That's all. Okay? Now, the arrow down below is going to give us another point. That point is very simple, and that is that volume and velocity are tied hand in hand. As one gets affected, the other is going to be affected. So it's very important that you understand volume and velocity. What we're telling you is this. The purpose of a pump, and we learned this back in basic hydraulics 1 and 2, the purpose of the pump is to increase the velocity of the water and then change that velocity into pressure. So we're seeing a change in energy form. All right? So if velocity is an energy form, and it can be, there's a formula that you can turn velocity into energy. So velocity is an energy form, and volume and velocity are the same thing. If we say to you that as the velocity goes up, the pressure goes down, we could also say to you, if the volume goes up, the pressure goes down. And of course, again, back in basic hydraulics 1 and 2, we talk about that pump curve, and piece of pipe here. And, of course, it's a little handwritten drawing there that I did. And in that piece of pipe, we're going to show you what we call the velocity curve. Velocity curve. Now, the velocity curve is showing us that right at the edge of the pipe, now this is on the inside of the pipe, right at the very inside of the pipe, where the water is touching the pipe, there's no movement, or very, very little movement, okay? And again, it doesn't matter what kind of pipe it is, whether it's plastic or steel, there's not a whole lot of movement because that water is clinging to the edge of the pipe. Now, the good news for us is that water has another term that we use called viscosity. Viscosity. Viscosity means the ability of a fluid to cling to itself. The ability of the fluid to cling to itself. So if you take the viscosity of water, which is 1, you'll see there's not a lot of viscosity there. So because there isn't, what that means is the water that's actually moving over that first layer that's touching the pipe can move a little faster. And then the next layer can go a little faster and a little faster and a little faster until you get to the middle of the pipe. Now, once you're in the middle of the pipe, now you've got the fastest moving water. So when we talk about a velocity curve, that's what we're looking at. When we talk about the turn velocity to you, we're simply mentioning the fact that there's water in the middle of the pipe. That's what we're talking about. All right? Now, the next slide that we see here is going to show us a 400-foot length of 2-inch pipe. Now, this 2-inch pipe is perfectly horizontal. Okay? And, of course, you have to remember that there is an inlet. It's 2 inches on each end. Okay, so whether you're looking at the inlet or whether you're looking at the outlet, it's 2 inches. All right? And if we were to put 40 gallons a minute in that inlet, so I'm going to put 40 gallons in. The question is, how much am I going to get out? 400 feet later, perfectly horizontal, how much water is going to come out of there? So if there's no place else for it to go, if I'm putting 40 in, it means I have to get 40 out. So 40 is going in, 40 is going out. All right? Now, of course, remember, we just saw that look of volume and velocity. So if we've got 40 going in and 40 going out, what that means then, if the volume remains the same and the pipe diameter remains the same, then, of course, there's something else that's going to remain the same, and that is the amount of velocity as the water moves through the piece of pipe. Remember, we can turn velocity into energy, so you can see there, I've marked it with a VE, velocity energy. And that velocity energy must remain constant the full 400 feet. It can't change because the flow doesn't change and because the pipe diameter doesn't change. All right? Now, there are 3 types of energy in a piece of pipe of moving water. Velocity energy is only one of them. Another type of energy is called pressure energy. So we'll put PE in there for pressure energy. Remember now, depending on our velocity, we're going to get something called friction loss or friction energy. And so the next thing we'll put in there is friction energy. And I want you to note something very, very important. I'm going to put a little green line on one end, and then go right straight up and put another green line there. And of course, that's the amount of pressure energy going into pipe. Now, if you go over to the right side of the picture, and we put those two green lines in, you will notice that there's not as much pressure energy coming out. So what this is helping us to understand is that friction energy, being a form of energy, has to convert from something else. Since it can't convert from velocity because velocity has to remain constant, the only other place for that friction energy to come from is the pressure energy. Every once in a while, I'll get someone that will say to me, "No, Bill, you're wrong. I know that if I use 1.5-inch pipe, I'm going to get more pressure out of it." Now, the reason that they think this is because they were in their garden one time, they had their garden hose, the hose was stretched as far as it possibly could stretch, and they couldn't get any more water going farther until they took their thumb and put their thumb over the end of the hose. When you do that, there are certain things that are happening. One of those things that are happening is because you're making the hole smaller, a smaller amount of water can come out. And because there's a smaller amount of water coming out, that means that the hose from your thumb all the way back to the source, the pressure is going to build up in that hose. Okay? Now, of course, that also means that what's coming out of the hose, because it is a smaller amount of water and it has a higher pressure behind it, is going to be higher velocity water. But all they're thinking about is the fact that if they make that hole smaller, they're going to get more pressure. And the answer is no, you're not really. Okay? Because what really happens is this. All right? If you look at the left-hand side there, notice that our incoming pressure has decreased. And, of course, if you look at the right-hand side, you'll see that our exit pressure has really decreased a lot. Okay? And the reason is the velocity energy increased. And so because the velocity energy increased, it means that there was more friction loss because we had more velocity. And we're going, wait a second, I didn't see the velocity line move. How can you make that statement? So we're going to get rid of the friction energy. And we're just going to talk about the energy, the velocity energy, the pressure energy as it enters the pipe. Okay? So if we take a close look, this line represents the velocity energy as it enters the 2-inch pipe. That line represents the pressure energy in the 2-inch pipe. Now, if we add both of those together, we're going to find 100% of all the energy going into the 2-inch pipe. Now, what I want you to do is I want you to look at that and tell me what percentage is the velocity energy of the total 100% energy in that piece of pipe. About 20%. Yep, right? Now, remember, we had somebody telling us that if they did 1.5-inch pipe, they'd get more pressure. All right? We're going to have to prove them wrong. So this is the velocity energy in the 1.5-inch pipe. This is the pressure energy in the 1.5-inch pipe. And once again, if we add those two together, that's going to be 100% of all the energy going into the 1.5-inch pipe. So now, of course, the question is, what percentage is the velocity energy in the 1.5-inch pipe compared to the 100% energy that is in the 1.5-inch pipe? So we'll call it 30 to 33% more. Okay? So, of course, the line representing the velocity didn't move, but because we've had an 1.5-inch pipe, you can see the 1.5-inch pipe is higher than the 2-inch pipe was, so our 100% energy moved. And so even though they may not have seen it, that's what happened with the velocity energy increase. We went from about 20% to about 33%. The next slide here indicates what happens when you go into an elbow. All right? And of course, you have to remember that there is momentum. And the momentum forces the elbow, or forces the water into the outside edge of that elbow. Now, as the water hits that outside edge, you're going to notice that it's going to wind up with higher velocity. And of course, the opposite of higher velocity is going to be lower pressure. However, if you look at that area on the inside of the elbow, because there is less water moving through it, we're going to wind up with a lower velocity, which means, of course, we're going to have a higher pressure. And that's what happens when water is forced to change direction by using an elbow. All right? We actually make the area, because the water wants to go straight, we actually make the area that the water is moving through smaller. Because that area is smaller, you wind up with higher velocity and lower pressure. So the next slide we're going to look at here, if you have your Stay Right, Berkeley, the new Myers catalog, or an air motor catalog, you're going to find this. This is the head loss chart. It's usually in the back of the book. Okay? So you'll notice here that we do make a recommendation, and the recommendation we make is keep the velocity below 5 feet per second. If you really feel you have to, go to 7. Now, I'm going to tell you right now, if you get too much above 7, right, the 10 feet per second range, you do start running a risk of having cavitation at an elbow. Now, the cavitation will happen at the elbow, but the cavitation damage happens downstream from the elbow. Oh, depending on what size elbow it is, it could be a couple of feet. Okay? So you have to watch for that. Keep that velocity down. Now, you'll notice that we have got 7 pipe sizes here. It starts out with 1/2 inch, and then it goes to 3/4, 1, 1 1/4, and then it goes to 1 1/2, 2, and 2 1/2 inches. Okay? All of those 7 pipe sizes have 5 columns in them, and that first column says flow in U.S. gallons per minute. The second column is just a little bit misleading because it says velocity, plastic, feet per second. Anybody who is a logical thinker is going to say to themselves, well, geez, if that's the velocity in plastic pipe, then the velocity in steel pipe must be different. And the answer is, yes, it is. But it's only different by a very, very small amount. And so because it's different by only a very, very small amount, it simply means that you're not going to see any difference. Okay? So in this book where it does say velocity, as far as I'm concerned, you can cross off the word plastic, because what really matters here isn't the type of pipe, but happens to be the ID of the pipe. And so if you look at the next 3 columns, the middle column says plastic pipe, gives you a C value of 140, and it gives you an ID of 6.22. The next column says steel pipe, has a C value of 100 with an ID of 6.22. And the third one has copper pipe with a C value of 130 and a ID of 6.25. So because those IDs are the same, the velocity, as far as we're concerned, is going to be the same. You won't be able to notice the difference in them. Now, if the IDs are different, then yes. And of course, who knows the difference between Schedule 40 and Schedule 80 PVC? What's the difference in them? Schedule 40, Schedule 80 PVC. Nobody knows the difference? wall thickness, the wall thickness. The outside diameter stays the same, but the wall gets thicker as your pipe gets heavier. And so, of course, as the wall gets thicker, what that means is that you're going to have a smaller ID because the OD stays the same. So because you have a smaller OD or a smaller ID, it also means that you're going to now increase that velocity, and that will change the friction loss. So what we want you to do in the chart here is we want you to look, and you'll notice in the velocity column at 4.5 gallons a minute, my velocity comes up to be 4.8. My friction loss in plastic pipe, very important to understand, we're talking about plastic pipe here, in plastic pipe is 18.3. Now let's do a little math, okay? Our math says that if we take 18.3 and we divide it by 2.31, and again 2.31 was the number that we learned in basic hydraulics 2 that taught us that we could go from pressure to feet of head. So we divide the 18.3 feet of head by 2.31, and we find the number of pounds of pressure. And of course, that's going to come up to 7.92, which of course we're going to round up to 8. Now, we're going to take a little break here and just show you something. And what we're going to show you is this. We've got a 100-foot long piece of pipe. Okay? Now, it's 1/2 inch schedule 40, which we were just talking about. 1/2 inch schedule 40 plastic. What we're going to do with this pipe is we're going to put 4.5 gallons in on the left-hand side. Of course, what that means is on the right-hand side, I'm going to get 4.5 gallons out, because where else can it go? It can't go anyplace. Okay? If on the output I want 50 psi, that means that on the input, what do I have to do? Raise your hand. And just tell me. What has to happen? If I want 50 psi in the output, I'm going to lose 8 psi going through the piece of pipe. What do I have to do in the input? Now, I thought that was an easy question, because I gave you the answer. 50 plus 8 equals 58. So it means that on the input, with my 4.5 gallons a minute, I have to put 58 psi. Because 100 feet away, I'm going to lose 8 psi. So if I want 50 over there, I got to put 58 in here. So now we'll go back to our chart again. Because remember we said if you really, really wanted to, and we are going to really, really discourage you, but if you really, really wanted to, you could take that velocity up to 7 feet per second. So if you look in the book, if you've got the book there, to get in the second column as close to 7 feet as possible means that we're going to be at 6.9 feet per second. 6.9 feet per second. I've got another question for you here. What did I increase my flow by? I went from 4.5 to 6.5, so I increased my flow by 2 gallons a minute. What happened to my friction loss in my plastic pipe? I went from 18.3 to 36.2. That's double the friction loss. Okay? So here's my 100-foot piece of pipe again, 1/2 inch schedule 40. I'm going to increase my flow now to 6.5 gallons a minute. Okay? So I'm going to put 6.5 in, and of course, I'm going to get 6.5 out. All right? Now, once again, on the output side, I still want 50 psi. So if I want 50 psi there, what do I have to do on the input? I've got to put in at least 66. Very important to understand that. If you know what the velocity and friction loss are at one point, on one side of the pipe, and then you double the flow on that side of the pipe, you know you're going to double your velocity. So it's very important. You can just take the percentage of flow that you're going up by, multiply that by your velocity, and you're going to see you're going to wind up. If you get double velocity, it's just going to really make things nasty. Okay? So this is why we strongly encourage you to try and keep that on a lower level. All right? Now, of course, if you think that's bad, take a look at what happens in steel pipe at 6.5 gallons a minute. All right? Your friction loss now is 67 feet of head. Okay? So once again, we're going to go back here. Only we're going to change that half-inch Schedule 40 PVC out for half-inch steel pipe. Okay? So we get rid of the PVC, and we put in steel. All right? Now remember, we're still going to put 6.5 gallons a minute in. And of course, if I put 6.5 in, what am I going to get out? 6.5 gallons a minute. Got no place else to go. All right? But of course, the question is, if I still want 50 psi over on that discharge side of that pipe, what has to happen on the input side? I now have to have almost 80 psi because I am going to lose almost 30 psi just pushing the water through that 100 feet of pipe. Now, the scary part about this is it's every 100 feet of pipe. And that's why this topic is so very, very important, so that we understand the losses that are being incurred. Why? Because somebody's got to pay for those losses. We've got to get the energy to get the water where we want it, the pressure we want it. Otherwise, we're not going to get the job done. So that's why it's so important that we understand these losses. Okay? Now, we're going to take a look at this next slide here. And this comes out of our Ag and Industrial book. And it comes out of, it's actually out of the B9020, Earth Engineering Manual. And what I've done is I've kind of chopped it up and put it together, okay? You can see the first column is your flow rate, the second column is 2-inch PVC, the third column is 4-inch PVC, and the fourth column is 4-inch ID steel pipe. Each of the pipe sizes is divided into two columns. One is velocity in feet per second, the other is your head loss per 100 feet of pipe. All right? Now, we're going to talk about 200 gallons a minute. That is a lot of water. Okay? When you try and put 200 gallons a minute, and yes, I just talked to someone last week that was talking about doing exactly that, and I said, whoa, I don't think that's a good idea. Notice what your velocity is at 200 gallons a minute through 2-inch PVC, 19.1. At your first elbow, I will guarantee you're going to have cavitation problems at that first elbow, okay? When you double the size of the pipe, you quadruple the area that that pipe has. And so, of course, as you quadruple the area, it means that you're going to quadruple less the velocity. So, as I go up in pipe size, my velocity goes down by quadruple, and you can see I'm 5.11 with plastic pipe. Now, I mentioned this earlier. I'm going to point it out again. This comes right out of our V9020. So if you've got it, you can follow along. The PVC pipe is on page 8. The steel pipe that we're looking at here now is on page 3. So if you've got the V9020 and you want to follow along, please do. All right? You're going to find that the steel pipe has a velocity of 5.05. So the difference between PVC and steel, they have the exact same ID, The difference in velocity is 6/100ths of a foot per second. Anybody on this call think they can notice the difference of 6/10 and 6/100ths of a foot per second? Not unless you got special equipment. Okay? There is a big change though, and you'll notice that if you look at the 4-inch ID steel pipe, the friction loss is going to be 4.3. Now take a look at the PVC. Because the PVC is a smoother material, because it's denser, your friction loss is about half. So even though the velocities are almost identical, the friction loss is half, and that's one of the things you need to take into consideration when you are considering plastic pipe. All right? So very, very important that you take a look at that. All right? Now, we're going to talk two things here. We're going to talk suction lift, how to calculate total suction lift, and of course, how to calculate friction loss. So what we've got here is we've got a customer who's got a pump sitting on the end of a pier. All right? He's got some pipe leading down into that water. That pipe happens to be 10 foot in length. Now that's overall linear feet of pipe is what we're looking at. Okay? From the surface of the water to the datum plane of the pump is going to be 4 feet. All right? Now, the question is, what is the friction loss at 20 gallons a minute in 1.25 PVC pipe? So if we look in our dealer catalog, towards the back of the book, we're going to find that the answer is 6 feet per 100. So if you try to put 20 gallons a minute through 1.25 PVC, you're going to lose 6 feet per 100. Now, let's calculate our friction loss. There's a reason why we got to calculate the friction loss first. Okay? The reason we're going to calculate the friction loss first is because friction loss is part of our total suction lift. So we have 10 feet of pipe, which is 1/10 of a 100-foot length. We're going to multiply that 1/10 of a 100-foot length times a friction loss of 6 feet per 100, and that gives us, in that 10-foot piece of pipe, a little over half a foot, 6/10 of a foot. Okay? So now, total suction lift. Let's talk about that for a second. Total suction lift includes two things. It includes the vertical distance from the water to the datum plane, and it includes the friction loss. So if I add those two things together, my total suction lift is going to equal 4.6 feet. All right, now once again, this is a true story also. So what happens here is this. As time goes by, the lake winds up having a drought, a 3-year drought. And in that 3-year drought, you're going to notice that the water has dropped considerably. Okay? As a matter of fact, the vertical distance that the water dropped is a total of 6 feet. So if we had 4 feet to start out with, and we're adding 6 feet to it, that now means that our total vertical lift is 10 feet. And I want you to understand something, and that is this. There is only one way to correct vertical lift, and that is to physically put the pump closer to the water. So if we physically put the pump closer to the water here, you're going to notice that once the water comes back and we're not around, we now have an above-ground pump that is submerged. The secret here, they don't work very well when you submerge an above-ground pump. So we really need to leave the water or the pump where it is on the dock there. Okay? The problem comes in, if you look real carefully, where's the suction pipe? out of the water. So now we have to add some suction pipe. Now I want you to know it's not just a matter of getting to the water. It's a matter of going off far enough out in that lake so that we can get the pipe under the water. And it needs to be under the water by at least 6 pipe diameters. So if we're using 1 1/4 pipe here, we need to be at least 9 inches under the water. Okay? To do that in this application took us 100 feet of pipe. Okay? So now we've got 100 feet of pipe here instead of 10 feet of pipe. Now remember, if we leave it at 1 1/4, our friction loss is going to be 6 feet per 100. So, again, if we do our multiplication here, we take 100 feet of pipe, which is 6 feet, plus our vertical distance, which is now 10 feet. That's going to make your total suction lift 16 feet. Now you've got a total suction lift here of 16 feet. Okay? So the question is, can we fix some of this? Well, we already decided that we can't change the vertical. But can we change the friction loss? The answer is obviously yes, otherwise why would we bring it, right? So, how do I fix some of this friction loss? I start going to bigger pipe. So if we look at 1 1/2 pipe, all right, what will the friction loss in 1 1/2 pipe be? And again, if you look in the back of your dealer catalog, you're going to find it's 2.83 per 100. Notice what we just did? By going from 1 1/4 to 1 1/2 pipe, we just cut our friction loss in half. Okay? Because now our total suction lift went from 16 all the way down to 13. All right? And that's just by going up 1 pipe size. So, of course, the question is, can we do better? All right? Well, let's find out. Let's go to 2-inch pipe. What is the friction loss in 2-inch pipe? And if you look at the friction loss in 2-inch pipe, you're going to notice, and again, we're in the Stay Right catalog, the Airmotor catalog, the Myers catalog, the Mercury catalog. It says 0.839 per 100 feet. All right? So now my total suction lift just went from 16 to 11 feet. Anybody ever look at a box chart before? Because if you look at a box chart is in 5-foot increments. We just say 5 foot, which means if you look at a box chart, the deeper it is to water, the less water you get. So we just gained some water back. We just made this pump work better, easier. Okay? But of course, can we do better yet? Well, let's take a look and see. And so now what we want to do is we want to move to 2.5 inch pipe. So if we put in 2.5 inch pipe, what is the friction loss per 100 in 2.5 inch PVC? Now notice we're keeping the pipe type the same, so we can compare apples to apples as far as friction loss is concerned here. And we're going to find that the friction loss in 2.5 inch pipe is 0.353. So our total suction lift, if you round things off, is going to be about 11, which was the same as it was before. Okay? So the question now comes up is, did it really make a difference at this point to put in the next size larger pipe? And the answer should obviously be no. It made no difference at all. So if it didn't make any difference to put in a larger piece of pipe, What did we just learn then? And what we just learned is this. Now watch the wording on the answer here. We just learned that two pipe sizes larger than the pipe size at 5 feet per second makes fractional pipe sizes most efficient. Makes fractional pipe sizes most efficient. And this is very important to understand this, okay? Because fractional pipe sizes mean ½ inch, 3/4 inch, 1 inch, 1.25 inches, 1.5 inches, 2, 2.5, 3, 3.5, 4. Those are fractional pipe sizes. Those are your smaller pipe sizes. Once you get into bigger pipe sizes, they start going by 1 inch, 2 inch sizes. And of course, now you're not going to see that difference. So when you're talking about your smaller fractional pipe sizes, you're going to find that, yes, indeed, two pipe sizes larger really helps you to keep your friction loss to a minimum. Okay? So what we're really trying to encourage you here is this. When you're doing a suction side of the pump, we put in a certain size hole. If you're using a straight centrifugal pump, the discharge hole will be one size smaller than the suction hole. All right? What we're telling you is go up 2 pipe sizes. It doesn't hurt to do it on both sides. On the suction side, you saw you were saving energy as far as we could now lift more water and make the pump work more efficiently. On the discharge side, yes, you're saving more energy there because you're reducing the friction loss, which increases the pressure at the end of the pipe, and may, doesn't always happen, but it may wind up having you use a smaller horsepower pump. All right? Now, a simple little example that we always do in our factory schools is this. If you take 1 inch pipe and you put 10 gallons a minute through it, what is the velocity going to be in feet per second? And of course, we have you go to the back of the book. In the back of the book, you find that the velocity here, now, we're coming up with the back of the book. All right? So this is what the 1 inch pipe chart looks like. All right? And of course, you're going to notice here that it gives us a couple of different columns. The first column there is our flow in U.S. gallons per minute. The second column there is our velocity in feet per second. Okay? So once again, if we go down to 10 gallons a minute, you're going to notice that our velocity is 3.7. Now, so we put that answer in, and then what winds up happening? Well, we ask another question. The next question is, what happens if I put 20 gallons a minute through the same 1 inch pipe? So we'll go back to our columns again here. And again, we're looking at those two columns there, the flow and the velocity column. And you're going to see at 20 gallons a minute, how to get there, okay? At 20 gallons a minute, our velocity comes up to be 7.4. 7.4 at 20 gallons a minute. Okay? So what we're going to do is we're going to go back to our problem here again, and we're going to put that answer in. All right? Now that you got your two answers in, the first answer number was 3.7, the second answer was 7.4, let's take a look at something. Let's take a look at the volume and velocities. If you look at the two volumes and velocities here, what do you notice? You notice that if you double the volume, you double the velocity. This is true for most of your pipe sizes in the building. You double that volume, you're going to come really close to having that velocity. Very, very important, because remember, when you double the velocity, you also wind up doubling your friction loss, and that really starts to get nasty after a while. So that's why it's so important that we understand and keep that velocity down. All right? Now, if you have the training manual, it's either on page 12 or 13, you're going to find a chart. And what the chart does is this. I've gone through and I've written down the flow rates through the different pipe sizes from 3/4 all the way up to 3-inch, and what those pipe sizes will carry at about 5 feet per second. Okay? Now, of course, if you look there, 3/4 is 8, 1 inch is 12, 20 for 1 1/4, 30 for 1 1/2, 50 for 2, 70 for 2 1/2, and 110 for 3-inch pipe. All right? So if someone starts talking about wanting to do 200 pounds a minute, let's check it. 2-inch pipe, not a good idea. Not a good idea. All right? Now, of course, some of you have this. And, of course, what this is the ruler that I produced. All right? And you can see on one side of the ruler, there is the Pentair logo. Okay? It tells you what 6 inches is. And you'll see there's the Pentair logo there. All right? On that side, it says inches of mercury, and right next to it, it says feet of head. So basically what we've done is we've said, okay, we're going to take what a vacuum gauge would do and convert that into feet of head. Why do you need to know that? Because if your vacuum gauge is reading 21 inches, you'll notice that that's about 24 feet of head. So what is the vacuum gauge telling you? It's telling you, I think I'm 24 feet off the surface of the water. You take the ruler and say, with a dumb vacuum gauge, you're only 2 feet off the water. But the vacuum gauge is saying, yes, that's true. But I'm doing so much work that it feels like 24. That's how hard the pump has to work. Now remember, the deeper I go to water, the less water I get. So what it's telling me is the pump is having a hard time getting water to it. There's two things that might cause that to happen. One, of course, is the most obvious, and that is friction loss of the piping system. That's what we were just talking about. Usually that's not the problem. Usually the problem is something is plugging up the suction. If we're pumping out of a lake or something like that, maybe a leak floating by got pulled into that suction screen, wrapped around the suction screen, and plugged off a whole bunch of holes. And now that pump is working harder. Now, of course, the opposite is true too. If I'm 2 feet above the water and I'm only registering 1 inch of mercury, that would tell me something too. What that's going to tell me is I have a suction leak. So very important to understand that's going to indicate to me a suction leak. If you flip the ruler over on the other side there, you're going to see it says pounds of pressure, feet of head. Now, what this side of the ruler is doing is it's measuring the discharge side of the pump. Okay? So, if I were to say that I want 50 psi, and I look down there, 50 psi comes up to 115.5. Generally, I round that off to 115, 116 feet. All depends on what I'm talking to. Okay? But I want you to know, all that really good, useful information is not the reason I gave you the ruler. The reason I gave the ruler is right here. You'll notice there it says pipe size, and then it says flow at 5 feet per second. And it starts out with 3/4 inch pipe and goes all the way up to 8-inch pipe. So we're really giving you some good help here with this ruler. If you haven't got a copy of it and you would like a copy of it, you need to let me know, and I can mail you a copy of it. All right? BillCorey@pentair.com is my email. If you want one, that's where you got to send it. All right, we're almost done here now. We're going to work one problem though here. The problem says we got 1.5 inch plastic pipe carrying 25 gallons and 235 feet. All right? There's 4 things I need to know. One of those things is velocity. To calculate velocity, I need to know the flow rate and the size of the pipe. Of course, we're assuming here that if we're going to use steel pipe or plastic pipe, it's going to be schedule 40 and schedule 40, so we don't have to worry about it, okay? So the bottom line is, if we would look this up, we would come up with a velocity of 3.9. The next question we're going to ask ourselves is, if you look in the book, what is the friction loss per 100? Now, of course, in order to calculate this, we need to know what our total length of pipe is. Excuse me, we need to just look at the book. So we look in the book, and we have to know what kind of pipe we're using, plastic or steel. So you can see here we're doing 25 pounds a minute, inch and a half plastic. So the friction loss in plastic pipe per 100 is 4.26. Now we need to know the total length of pipe, because we're going to take that total length of pipe and we're going to divide it by 100. Because remember, the chart is in 100-foot lengths. So if we divide 235 feet of pipe by 100, that's going to be 2.35 100-foot lengths of pipe. Now remember that total length of pipe is going to equal not only the linear feet, but the equivalent feet of pipe, straight pipe for elbows and fittings. We'll talk about that in a second. All right? Now we just have a simple math problem. We multiply 4.26 feet of head loss per 100 feet of pipe times our 2.35 feet of pipe, and we come up with an answer of 10.01. Now, once again, we want you to convert this to pressure because most people understand pressure a little bit better. So if we take the 10.1 and divide it by 2.31, we're going to come up with a pressure loss of about 4.3 pounds of pressure. All right, that's about what we're losing. Now, if we do the exact same problem, the only thing we're going to change in our problem is the diameter of that pipe. We're going to put an inch and a half, inch and a quarter. Okay, so from inch and a half to inch and a quarter. Our velocity now jumps up to 5.4. It's greater than 5, but less than 7. Let's see what happens. Okay, our friction loss per 100 now, well, again, if you look that up in the book, you're going to see that it comes to 9.06. 25 gallons a minute for inch and a quarter pipe, 9.06 per 100. I did not change the length of pipe whatsoever. So it still comes out to be 235 feet of pipe. So I divide the 235 by 100, and it comes out to be 2.35 100-foot lengths of pipe. Again, it's now just a simple math problem. I multiply 2.35 100-foot lengths of pipe times 9.06 per 100, and I come up with a total friction loss of 21.29. Now, once again, because most people think in terms of pressure better than they do feet of head, which I guess if it was me, I'd say shame on you because I'm a pump guy. Pump guys talk feet of head. But if you don't, that's okay. We'll get you used to talking about it. You take that 21.29, you divide it by 2.31, and that comes up to about 9.2 psi. Now notice what we did. We went down one pipe size. And by going down one pipe size, we more than doubled our friction. We went from 4.3 to 9.2 psi. All right? And that's the point that we're really, really trying hard to get across to you. All right? Now, one more thing we have to learn, and that is that equivalent length of pipe. So we're going to pull up that friction loss chart again. Again, if you've got a dealer catalog, whether it's Stay Right, Berkeley, or Motor Myers, doesn't matter. Look in the back of the book, and you're going to find the friction loss charts. On the bottom of the friction loss chart, it talks about the equivalent length of pipe. And notice that it says friction loss through fittings in terms of equivalent length of pipe. All right? Now you'll notice that there is a chart there. I chopped the chart up. I only went to inch and a quarter because it makes it big enough so you can see it. And I've left out three pieces of pipe, three different types of fittings. One of them is that standard 90. So if you take that standard 90, look at the plastic version of it, you'll notice that that's blank. If you were to fill in the blank, you would notice that it comes up to 7 feet. Now remember, it is not 7 feet of head, it is 7 feet of straight pipe. If you were to have a standard T in plastic, it would equal 12 feet. Again, this is 12 feet of straight pipe. And the last thing that's there is the gate valve, and the gate valve is going to equal 5 feet straight pipe. All right? So we've gone through, we've taken these fittings and we've turned them into equivalent length of straight pipe. Now it's just a matter of adding it all together. I want you to know one thing though. If you're looking at the elbow or if you're looking at the standard T, we found earlier that plastic pipe had less friction loss by about half of steel pipe. However, you will notice here that in your plastic pipe, you're getting more equivalent length of straight pipe. The reason for that is because when you look at an elbow that's plastic, you'll see it's a true 90. When you look at an elbow on a steel pipe, you'll see it makes a nice sweeping curve. And so therefore, it's not quite as bad. All right? Very important that you note that. Now, our last problem here. We're going to take and we're going to put some fittings into our system. Okay? So notice that we have an 1¼ inch plastic pipe carrying 20 gallons a minute, 275 feet with these fittings. 3 standard elbows. We said that each elbow was 7, so 3 of them are going to equal 21. 2 standard T's. A standard T was equal to 12. 2 of them are going to be equal to 24. All right? A gate valve is equal to about 5 feet. There is only one, so that's going to be 5 feet. If you add all those equivalent lengths of pipe together, you're going to come up with 50 feet of equivalent length of pipe. The actual length of pipe is 275, so when we go to our friction loss chart, the effective length of pipe is going to be 325. Now remember that in your friction loss chart, you have to divide that by 100. So if I divide 325 by 100, I get 3.25 100-foot lengths of pipe. The friction loss per 100 in 1¼ plastic pipe at 20 gallons a minute, earlier we said was 6. So I multiply 6 times 3.25, and I come up with 19 and a half. 19 and a half feet of head. Now, of course, I'm not trying to trick anybody. And so I want you to understand that, yes, we do realize that you're only talking 50 feet of pipe. So let's take a look here. 0.5 times 6. 0.5 is the 100-foot length of pipe we've got there, just for the fittings. Times 6 feet of head loss per 100 foot is 3 feet of head. 3 feet of head is just a smidge over 1 psi. And most of us, we aren't going to worry about 1 psi, are we? Okay? So, of course, the bottom line is, if we were to now go ahead and calculate this, there's another way of doing it. The other way of doing it says, let's take the total amount of friction loss. So if I minus the 3 feet of head that I'm getting here from the 19 and a half that I got by doing the complete problem, I come up with 16 and a half feet of head. Okay? Again, I like to round things off, so I round that 16 and a half up to 17. All right? Now, if I take 10% of 17, 10% of 17, and that little oof that we're going to put in here is if you don't want to do all the math, just go ahead and take 10%. So 10% of 17 is going to equal 1.7. 1.7. Now I'm going to round that 1.7 up to 2. I like to round up just in case. And if I add that 2 to my 16.5, which we rounded off to 17, it gives me 19 feet of friction loss. It was 19.5, and now we're getting 19. You can see that the 10% rule works pretty much too. However, there's one thing to take into consideration. All of this is based on what we call 9 elbows. 9 elbows. Now, the reason that we're basing all of this on what we call 9 elbows is simply because of a fact. And it's an old lesson that's been taught in plumbing for quite a while, and that is that all based on the fact that 9 elbows equal a plug. Remember, if you got a plug, you're deadheading your pump. All right? So it's very important that we understand that.